Hi there, physicists. This is Mr. Clegg, and we're going to learn how to make a free body diagram Clegg style today. So free body diagram is a diagram of all the forces that are acting on a certain object. And for the purposes of making a free body diagram, you're going to assume that all the forces act on a point. So you're going to make the object into a point, which is represented by a dot on your diagram. And then you're going to put the forces on there with the tail of each vector on the dot. And you're not going to use any components. You're going to put some angles in there and label them if you need to. And if two forces are in the same direction, you're going to space them apart next to each other so that they can be seen clearly. So I'll give you an example of that. You're going to make a box to the side for the acceleration direction or 0. And same thing for the net force. And I'm going to show you how to do that. And just remember that net force and acceleration are always in the same direction or they're both 0. Sometimes you can discern one or the other more easily from the situation. Okay. All right, we're just going to go ahead and jump right into it here. So example 1, a ball is hanging from a string at rest. So we're going to make a dot to represent the ball. We're going to put the two forces on there that are acting. One is gravity going down, and we'll call that mg. Sometimes we call it F sub g, but sometimes we'll call it mg. And we're going to make a force going up for the tension. That's different ways of calling tension, but I'm going to call it F sub t for this one. And I like to use a pencil when I make a free body diagram because I don't know about the sizes of these force vectors yet. So I might need to erase and make something longer or shorter. And so in order to figure that out, I'm going to make my A and F net boxes over on the side. Now this is just hanging out. So it's not accelerating because it's at rest and it's remaining at rest. So it's got a 0 acceleration. And since it's got a 0 acceleration, it also has a 0 net force. And since it has a 0 net force, I know that these two forces have to be equal, so I'll indicate that here. And it looks like I might need to adjust this a little bit because I didn't really measure this, but you want to make it approximately equal on your drawing if it's, doesn't have to be to scale, but it should be kind of close. All right, let's go into the next example. A ball is hanging from a string at rest, but it's also being partially supported by a table. So the situation is almost the same here. We've got gravity going down. Maybe it's the same ball as in the previous example. I'll label it with a different symbol for gravity this time just to show you that you can do that. Fg. I actually prefer to do mg myself, but some people like to write with an Fg. And we have the tension going up, but we also have a force from the table pushing upward on it. That's the normal force. So we're going to have two forces. So now I get to show you how it looks when you have two forces in the same direction. We might have the tension force, and we have another force here with the normal force. Now we don't know which one is bigger from the situation. As described, we don't actually know which of these two forces in the upward direction is larger, but we do know that those two have to add up to the gravity force. How do I know that? I got ahead of myself a little bit here. Let's take a look. We have no acceleration still, and therefore we have no net force. And since we have no net force, we know that the up forces and the down forces have to add up to the same. So that's how I know that the two up forces have to add up to the down force. All right, we're going to go down to the next one. A puck is sliding along a table and is slowing down due to friction. So I'm going to make a side view of this puck. I'm going to make it into a dot here. There we go. I'm going to put gravity on there. And I'll call it mg again because I like that. Mass times acceleration due to gravity. And I might be a little stuck here. I'm not sure if I can think of other things, but I'm going to go ahead and do this part because I know that the acceleration is not 0. It's sliding on a table and it's slowing down. That means its acceleration is going back the way it came. I know it has to be going that way because I labeled the velocity on here. It's going to the right. If you had drawn it going in a different direction, that's okay. Just as long as your velocity and acceleration are in opposite directions because it's slowing down. All right, so we have acceleration to the left in this case, that means that the net force has to be in the same direction, so it's also to the left. Okay, so, all right, so that's interesting, and it could be a little bit of a clue. I know that since it's resting on the table still, it's got an upward force. Now I need to figure out how big to make this upward force. Right, that's the normal force going upward. Did I label my vectors up here? Yes, I did. And so I don't know if it's the same or not as the down force, but then it also has a friction force acting against its direction of motion. So, oops, let's try that again. There we go. So we have a frictional force. I'll call it lowercase f k for kinetic friction. All right, there are different ways to label that, but that's the way I'm choosing now. And then I realized that the net force is purely to the left. So that means this makes sense. We got a net force here, but that means there can't be any vertical component to the net force. So I have to go back and change this and make sure that the up force and the down force here are equal. So I'm going to make those two equal. Let's see if I can make that straight without it jumping. Oh boy. Something like that. There we go. So now I'm going to show that these two are equal. Okay. Finally, let's move on to the next one. A tether ball is moving around a pole at a constant speed in uniform circular motion. So let's represent the ball here with a dot. Let's put gravity on there first. I always like to start with gravity to make sure I don't forget. I'll put mg there. All right. And then I know I have a force from the tension, and that's pulling up at an angle here. Okay, that'll work. One of the things that I didn't do yet, and I probably should have in the problem statement, was indicate that there's an angle here. Right, there's an angle theta here. So when I go over here to this, I can actually see that this angle here, I'm going to indicate on my free body diagram a dotted line showing that there's not a force there, but I'm just showing that that's a vertical line. And this force, the tension force from the string, is acting at an angle theta away from the vertical. It's the same angle as this. So if you imagine, here's your vertical that I drew over here. And then this angle theta is the same as that angle theta. And the reason for that is, quick little detour back to, let's see. Okay, we have alternate interior angles are equal. So we're going back to geometry here. So these two angles are both equal because they're alternate interior angles. So this angle and that angle are both the same because you have two parallel lines and a transversal, in case you wanted to go back and see why that's the case. So those are the two forces we have. I have to think about now, do we need any other forces? Do we have any other forces? What about centrifugal force or something like that? Well, it turns out centrifugal force actually isn't a force. There's no force pushing it out that way. What about centripetal force? Centripetal force, well, that's just a component of this tension force. So if we were to break this up, we're not going to do it on a free body diagram, but when we break this tension force into horizontal and vertical components, the horizontal component of that is the centripetal force. But we're going to leave it like that because that would be, we're going to do the component thing later. So here's our acceleration. Which way do we have an acceleration in this case? Right at this moment, obviously it's going in a circle, but the acceleration is centripetal, so it's always going toward the center. So it turns out that the acceleration is, at this moment, going that way. And that means that the net force is also going that way. And does that make sense in terms of what I've drawn here? Do I have a net force shown to the right? Yes, I do, because it looks like a part of the component of this tension force, the vertical component, cancels out with the gravity, and the horizontal component is the net force going toward the center, which is the centripetal force. Hope this made sense. I hope you practice lots and lots of free body diagrams and ask me questions if you need it. All right, good luck. Have fun.